What if everything you thought you knew about reality was just the surface of something infinitely more profound? We're all familiar with the world around us, the three dimensions of space we move through, and the steady flow of time that carries us forward. But what if that's not the whole story? What if our universe is like a page in a book, and we've only ever been reading the words printed on it, completely unaware of the thousands of other pages, other dimensions, hiding just beyond our perception? This isn't science fiction. For decades, physicists and cosmologists have been wrestling with one of the most tantalizing ideas in modern science: the possibility that our reality is embedded within higher, hidden dimensions. These aren't dimensions you can see or touch, but mathematical and theoretical extensions of space and time that could answer some of the universe's deepest mysteries. Why is gravity so weak compared to other forces? What is dark matter made of? Could there be entire worlds existing right alongside ours, completely invisible to us? In this video, we're going to explore 30 of the most groundbreaking theories that attempt to unravel these elusive layers of reality. From the elegant mathematics of string theory to the mind-expanding concept of the multiverse, from curled-up dimensions smaller than atoms to vast, unseen realms that might govern the very fabric of the cosmos, we're about to take a journey that will challenge not just what you think you know, but how you think about knowing itself. So settle in, open your mind, and get ready to see the universe in a whole new light. Our journey into the hidden layers of reality begins not with complex modern equations, but with a quiet revolution that started over a century ago. In 1919, a little-known German mathematician named Theodor Kaluza was studying Albert Einstein's groundbreaking theory of general relativity. He saw in Einstein's elegant equations a hidden potential, a structure that suggested something was missing. Kaluza made a bold, almost heretical move. He took Einstein's work and rewrote it, not for the familiar 4 dimensions of space and time, but for a universe with 5. The result was nothing short of magical. From this single extra dimension, an entirely new set of equations naturally emerged. These equations perfectly described not only Einstein's gravity, but also the other fundamental force known at the time, James Clerk Maxwell's theory of electromagnetism. Kaluza had seemingly achieved the holy grail of physics, a unified theory. He sent his results to Einstein, who was initially stunned and perplexed. The idea was so beautiful, so compelling, that Einstein held onto the paper for 2 years before finally encouraging its publication. But a huge, obvious question remained. If there is a 5th dimension, where is it? Why can't we see it, move through it, or detect it in any way? This is where Swedish physicist Oskar Klein entered the picture a few years later. Klein provided the crucial missing piece of the puzzle. He proposed that this 5th dimension isn't like the vast, expansive dimensions we know. Instead, it is curled up or compactified into an unbelievably tiny loop, a circle with a radius smaller than a billionth of the size of an atom. To understand this, picture a long, thin garden hose stretching far into the distance. From a great distance, it looks like a simple one-dimensional line. But if you were an ant crawling on its surface, you would discover it has a 2nd dimension, a circular direction that curls around its circumference. Klein suggested our entire universe is like that hose. We are like creatures too large to perceive the tiny, circular 5th dimension curled up at every single point in space. Our instruments are too coarse to detect it, but its existence has a profound effect, giving rise to the electromagnetic force we observe. This Kaluza-Klein theory was the first serious scientific proposal that our reality is built upon more dimensions than we can perceive, a monumental idea that planted the seed for every theory of hidden dimensions that would follow. Kaluza and Klein had shown that adding just one extra dimension could beautifully unify the forces of nature, but their work was just the beginning. The next great leap forward would come from a theory so radical it proposed rewriting the very definition of reality's most basic building blocks. This is superstring theory, and it doesn't just add one hidden dimension, it demands 6 entirely new ones. For centuries, we've imagined the universe as being made of tiny, point-like particles, like indivisible specks of dust. Electrons, quarks, and photons were all thought to be these fundamental, zero-dimensional dots. But this picture leads to immense problems, particularly when we try to combine Einstein's theory of gravity with quantum mechanics. The math simply breaks down, producing nonsensical infinities. Superstring theory offers a breathtakingly elegant solution. It proposes that at the very heart of everything at the tiniest possible scale are not points but incredibly minute, vibrating loops of energy strings. These strings are so small that if an atom were the size of our solar system, a string would be no bigger than a tree on Earth. And just like a violin string can vibrate to produce different notes, a G, a D, an A, these fundamental strings vibrate in distinct patterns or modes. Here's the truly magical part. The specific resonance of that vibration determines what the string becomes. One specific vibration might manifest as an electron, another as a quark, and yet another as a photon. In this stunning vision, the entire symphony of the cosmos, every particle and every force, is generated by the harmonies of these tiny, oscillating strings. But for this cosmic melody to work, for the mathematics to be consistent and avoid those destructive infinities, the strings cannot vibrate in just our familiar 4 dimensions. The equations of superstring theory are only stable and make logical sense in a universe with exactly 10 dimensions, 1 of time and 9 of space. We clearly experience only 3 spatial dimensions, so where are the other 6? Following in the footsteps of Klein, the theory proposes they are compactified, curled up into an impossibly complex, tiny shape at every single point in our familiar space. These are not large, expansive dimensions, but are folded into a geometric form known as a Calabi-Yau manifold, a shape with intricate holes and tunnels existing at the Planck scale, a billionth of a billionth of a billionth of a centimeter. We are forever unaware of them because we are, in a sense, too large to navigate their contours, just as an ant crawling along a cable is unaware of the vast 3rd dimension that stretches away from it. The specific way these 6 dimensions are folded in on themselves would determine the properties of our universe, dictating the number of particle families, the strength of forces, and perhaps even why we have 3 familiar spatial dimensions instead of 2 or 8. Superstring theory doesn't just suggest hidden dimensions are possible. It argues they are an absolute mathematical necessity for reality to exist at all. But if you thought 6 hidden dimensions were complex, prepare yourself for an even grander, more unified vision of reality. The triumph of superstring theory soon revealed its own intriguing complication. Researchers discovered not 1 but 5 distinct, self-consistent versions of the theory. Each was a valid 10-dimensional framework, yet they appeared to be separate and competing descriptions of the universe. This was deeply unsatisfying for physicists seeking one single, fundamental theory of everything. The puzzle was finally solved in a monumental leap by physicist Edward Witten in 1995. He demonstrated that these 5 string theories were not rivals at all, but merely different facets of a single, deeper structure. He named this overarching framework M-theory, and it required a bold new addition to the cosmic blueprint, an 11th dimension. This new dimension isn't compactified and tiny like the 6 of string theory. Instead, it's a vast expanse, and it completely changes our perspective on the cosmos. Within this 11-dimensional bulk, the fundamental objects are no longer just one-dimensional strings. M-theory introduces 2-dimensional membranes, 3-dimensional blobs, and potentially even higher-dimensional objects, all collectively known as branes. Our entire universe, with its 3 spatial dimensions and all the particles and forces within it, could be one such three-dimensional brane, often called a three-brane, floating within this higher dimensional bulk. Imagine our reality as an immense, impossibly thin sheet of paper drifting in a cosmic wind, a membrane that traps the strings of our standard model particles like electrons and photons, so they can only vibrate along its surface. This is why we are forever confined to our three spatial dimensions. Everything that makes up our world is stuck to this brane. This revolutionary concept provides a stunning and elegant answer to one of physics' oldest questions. Why is gravity so unimaginably weaker than the other fundamental forces? A magnet can easily defy the gravitational pull of an entire planet, lifting a paperclip against Earth's immense weight. In the brane world scenario, the answer is that while particles and forces like electromagnetism are trapped on our brane, gravity, which is the curvature of spacetime itself, is not. It can leak out or propagate into the full 11-dimensional bulk. From our perspective on the brane, this dilution makes gravity appear extremely weak, as its true strength is spreading out into dimensions we cannot access. The gravitational pull we feel might just be a faint shadow of its full power, a tiny fraction of its influence that has seeped into our dimensional island from the greater cosmic ocean surrounding us. But if the idea of our universe as a membrane floating in a higher dimensional space seems like a wild abstraction, wait until you hear how physicists have given this concept precise, testable mathematical form. The true power of the brane world idea exploded onto the scene in 1999 with a groundbreaking paper by physicists Lisa Randall and Raman Sundram. They constructed an elegant and radical model that didn't just suggest our universe is a brane, it provided a stunning new explanation for one of the most stubborn puzzles in all of physics, the hierarchy problem, or why gravity is so spectacularly weaker than all other forces. The Randall-Sundram model imagines a 5-dimensional universe, a bulk, with our 4-dimensional universe, 3 of space, 1 of time, as one membrane embedded within it. But this isn't a flat, featureless bulk. Randall and Sundram proposed it is warped, profoundly curved by gravity, much like the space around a massive star but in an extra dimension. In their most famous scenario, there are 2 branes. Our entire observable universe, with all its stars, galaxies, and people, exists on one brane, often called the TV brane. Separated from us in this warped 5th dimension is another hidden brane, sometimes called the Planck brane. This warping of the geometry creates an exponential scale factor, a sort of gravitational redshift that drastically dilutes energy scales as you move across the bulk. Here's the incredible part: the fundamental scale of gravity could actually be just as strong as the other forces, but it originates on that distant, hidden Planck brane. By the time its influence crosses the warped geometry to reach our brane, it has been exponentially suppressed, making it appear trillions upon trillions of times weaker. Imagine a shout from someone on the far side of a vast, curved valley. By the time the sound waves travel across the warped landscape and reach you, they are barely a whisper. That's gravity in the Randall-Sundram model, a faint echo of its true power, dampened by the hidden geometry of an extra dimension. This elegant mechanism sidesteps the need for the extremely tiny, curled-up dimensions of string theory. The extra dimension in Randall-Sundram can be large, even infinite in extent, yet remain hidden because everything that makes up our world, except for gravity, is stuck to our brane. We are like characters in a painting, able to move around on the canvas but utterly unaware of the gallery that stretches off into the distance all around us. The only hint of that greater gallery is the mysterious, weak force of gravity that seems to seep into our world from somewhere else. This model isn't just a beautiful mathematical construction, it makes real, testable predictions. If gravity can leak into the bulk, then it might be possible for tiny, high-energy ripples in spacetime, gravitational waves, or even miniature black holes to be created in particle colliders like the Large Hadron Collider, providing our first experimental glimpse into the architecture of the cosmos's hidden dimensions. While the idea of warped dimensions offers one compelling solution, another group of physicists took a completely different and even more radical approach. What if the reason we haven't detected these extra dimensions isn't because they are warped or curled into impossibly tiny shapes, but simply because we haven't been looking on the right scale? This is the astonishing proposal behind the theory of large extra dimensions, put forward by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Georgi D. Volley, often called the AD model after their initials. Their theory starts by directly confronting the hierarchy problem, but with a breathtakingly simple premise. For over a century, we've assumed that the Planck scale, the incredibly tiny distance of 10 to the minus 35 meters where quantum gravity is believed to take over, is a fundamental constant of nature. But what if it isn't? Arkani-Hamed, Dimopoulos, and D. Volley asked a revolutionary question. What if the scale of quantum gravity is actually much, much larger, and therefore within reach of our particle accelerators? The only way this could be true is if gravity's apparent weakness is an illusion created by the geometry of hidden dimensions. Their model proposes that our universe has more than 3 spatial dimensions. It has several additional ones. But unlike the minuscule loops of string theory, these extra dimensions could be vast, perhaps as large as a millimeter across. To understand how this works, imagine the force of electromagnetism as a wave that can only travel along the surface of a lake. It is confined to the two-dimensional plane. Gravity, however, is like a ripple that can move through the entire volume of the lake, spreading out in 3 dimensions. Because the ripple's energy is dissipating through a greater volume, it appears much weaker at any given point on the surface. In this scenario, the true strength of gravity is not weak at all. At its fundamental scale, it could be just as powerful as the electromagnetic force, but from our perspective, trapped on our 3-dimensional surface or brane, we only experience a tiny fraction of its total influence. The rest of gravity's strength is bleeding out into these large, unseen dimensions that are literally all around us, just a fraction of a millimeter away in a direction we cannot point to or move in. This is why a small magnet can overpower the gravitational pull of the entire Earth. We're not feeling gravity's full force. The implications of this idea are staggering. If these large extra dimensions exist, it would mean that the fundamental energy scale of quantum gravity isn't an unreachable 10 to the 19th billion electron volts, but could be as low as 1,000 billion electron volts, an energy range already being probed by the Large Hadron Collider. This opens up the electrifying possibility that we could create microscopic black holes or detect gravitons, the hypothetical particles that mediate gravity, disappearing into these hidden realms. Experiments wouldn't need to be based on impossibly large planet-sized machines. The secrets of quantum gravity and the universe's hidden architecture could be revealed in a lab, changing our understanding of reality forever. Yet another profound implication of the brain world concept challenges the very origin of everything. What if the Big Bang was not a singular, explosive birth from a single point of infinite density, but something far more dramatic, a cosmic collision? This is the core of the ekpyrotic universe model, a theory emerging from the framework of string theory that paints a breathtaking picture of a cyclic cosmos forever renewing itself. The name ekpyrotic comes from the ancient Greek word for conflagration or out of fire, and it proposes that our universe began not with a bang but with a crash. In this model, our entire 3-dimensional universe is one brane, and floating parallel to it in the higher dimensional bulk is another, separate 3-brane. These 2 immense membranes are drawn together by the faint gravitational attraction between them, moving slowly along a hidden dimension. Imagine 2 enormous, perfectly flat sheets of paper drifting toward each other in a silent, dark room. Their eventual meeting is inevitable. When these two branes finally collide, the impact unleashes an inconceivable amount of energy. This violent event is what we perceive as the Big Bang. The immense heat and density generated in that collision create all the matter and radiation that would eventually form galaxies, stars, and planets. It wasn't an explosion from a single point, but a simultaneous, universe-wide ignition triggered by the contact of these two colossal structures. This provides a stunningly elegant alternative to the theory of cosmic inflation, which posits a period of faster-than-light expansion immediately after the Big Bang to explain the universe's uniformity. In the ekpyrotic scenario, the branes are nearly parallel and flat before they collide, which naturally gives our universe its observed flatness and smoothness without needing a separate inflationary epoch. But the story doesn't end with one colossal crash. After the collision, the branes bounce apart, filled with the hot, expanding plasma of a new universe. They then drift away from each other, slowly and almost empty across the vast bulk. The gravitational pull between them eventually halts their separation and draws them back together once more, setting the stage for another collision, another Big Bang, and the birth of a new cosmic cycle. In this vision, time has no true beginning and no ultimate end. Our universe is just the current iteration in an endless series of cosmic cycles, each beginning with a brane collision and ending as the universe expands and cools into a near void, only to be violently reborn again. This cyclical model offers a profound resolution to the puzzle of the universe's initial conditions, suggesting that the seemingly fine-tuned parameters for life weren't set at a one-time creation event, but were shaped and perhaps even inevitable across an eternal, repeating sequence of cosmic renewal. Yet each of these theories, from warped geometries to colliding branes, grapples with the nature of space itself. But what if the very idea of space as a volume is an illusion? This brings us to one of the most profound and mind-bending concepts in all of theoretical physics, the holographic principle. The story of this radical idea begins not with the birth of the universe, but with its most enigmatic endpoints, black holes. In the 1970s, physicist Jacob Bekenstein made a startling proposal. He argued that a black hole must possess entropy, a measure of disorder or information content. This was revolutionary because entropy is a property of systems with many constituent parts, yet a black hole was thought to be defined only by its mass, charge, and spin, appearing featureless and simple. Bekenstein and later Stephen Hawking showed that a black hole's entropy is not proportional to its volume, as one might expect, but to the surface area of its event horizon. The event horizon is the point of no return, the two-dimensional spherical boundary that shuts the black hole off from the rest of the universe. This discovery, known as the Bekenstein-Hawking formula, implied something extraordinary. All the information needed to describe everything that ever fell into the black hole, every star, every planet, every book, is not lost within its three-dimensional volume. It is somehow encoded, pixelated, and stored on the two-dimensional surface of its horizon. This bizarre connection between surface area and information content led physicists Gerard T. Hooft and Leonard Susskind to propose a staggering generalization. What if this isn't just a unique property of black holes? What if it is a fundamental law of the universe? The holographic principle suggests that any volume of space, anywhere, can be completely described by information stored on its lower dimensional boundary. A three-dimensional region of space is not its own master. It is a projection, a translation of data written on a two-dimensional surface that encloses it. To grasp this, think of a common hologram like the one on your credit card. A flat, two-dimensional surface is etched with microscopic patterns. When you shine light on it, it projects a fully three-dimensional image that you can look around. The illusion of depth is compelling, but all the information to create it is contained on the 2D surface. The holographic principle posits that our entire universe might work the same way. The three-dimensional world we live in, with its galaxies, oceans, and people, might not be the fundamental reality. It could be a magnificent dynamic hologram. The true, fundamental description of everything, the ultimate source code of reality, resides on a vast, distant, two-dimensional surface that surrounds us at the boundaries of the observable universe. Every event that happens here in the volume, every particle collision, every thought you have, is a translation of information processing happening on that remote cosmic screen. This idea finds its most precise mathematical realization in the AD/CFT correspondence, a discovery in string theory that provides a concrete example of holography in action. It demonstrates a perfect duality, a complete equivalence between a theory of gravity operating in a warped, higher dimensional volume and a quantum field theory without gravity that lives on its lower dimensional boundary. In this framework, the messy, complex physics inside the volume is exactly mirrored by the elegant, gravity-free physics on the boundary. They are two utterly different descriptions of the same reality. If this is true, it means that our perception of a three-dimensional world is a grand illusion, a holographic movie playing out for us, with the real actors and scripts existing on a flat stage we can never see. The line between what is real and what is information becomes impossibly blurred, suggesting that at its most fundamental level, the universe might not be made of particles or strings, but of bits. But if the holographic principle suggests our reality is a projection, another theory proposes an even grander form of cosmic recycling, one where the universe itself is reborn in an infinite cycle. This is conformal cyclic cosmology, or CCC, the brainchild of Nobel laureate Sir Roger Penrose. It's a theory that completely reimagines the ultimate fate of the cosmos and its origin, weaving them together into a single, breathtaking tapestry of eternity. For decades, the standard view of cosmology presented two bleak options for how our universe might end. The Big Freeze, where it expands forever into a cold, dark, and empty void, or the Big Crunch, where it collapses back in on itself in a fiery reversal of the Big Bang. Penrose looked at the first option, the heat death of the universe, and saw not an ending but a transformation. He realized that in the far, far future, when the universe has expanded to such a degree that it contains almost nothing but a sparse sea of radiation and a few stray particles, something remarkable happens. All matter will have eventually decayed into light, and all massive particles will have been swallowed by black holes, which themselves slowly evaporate over eons due to Hawking radiation. In this state, the concept of scale and distance becomes meaningless. There are no rulers or clocks left to measure anything. The universe becomes smooth, featureless, and timeless. This is where Penrose applies a mathematical concept known as conformal rescaling. Imagine taking a detailed map of the world and shrinking it down so that the entire planet is the size of a marble. The map is still perfectly accurate in its proportions, the shapes of the continents are preserved, but all sense of absolute distance has been lost. Penrose's profound insight is that the infinitely vast, exponentially expanded, and utterly empty future of our universe is mathematically identical to the incredibly hot, dense, and tiny singularity of a Big Bang. They are conformally equivalent. In this smooth, energy-less state, the end of time for one universe simply becomes the beginning of time for the next. The remote future of one cosmic cycle, or aeon, becomes the Big Bang of the succeeding eon in an infinite sequence without beginning or end. This leads to a staggering implication. Information from our eon could, in principle, cross over into the next. The violent events of our universe, like the collisions of supermassive black holes, would generate ripples in spacetime known as gravitational waves. Penrose and his colleagues have suggested that these waves, traveling across the universe, could leave faint, circular imprints in the cosmic microwave background, the afterglow of our own Big Bang. He believes we may have already detected these Hawking points, which would be nothing less than echoes from a universe that existed before our own. If true, this would represent a form of dimensional transcendence, where information from one complete cosmic cycle somehow bridges the gap to structure the beginning of the next, creating a cosmic inheritance written in the very first light of creation. So we've seen how extra dimensions might be hidden, curled up, or warped, and how our reality could even be a holographic projection. But this next theory asks an even more radical question. What if dimensions aren't fundamental at all? What if the four-dimensional spacetime we call home isn't a fixed, pre-existing stage, but something that slowly congeals into existence from a more primitive, lower-dimensional chaos? This is the fascinating proposal of causal dynamical triangulation. Imagine you're trying to map out an incredibly complex, bumpy landscape, but you don't have a fancy topographical survey kit. All you have are a bunch of small, flat triangles. By carefully fitting these triangles together, edge to edge, you can gradually build up a surface that approximates the curves and hills of the real terrain. The more triangles you use, the smoother and more accurate your model becomes. Causal dynamical triangulation applies this exact same logic to the fabric of spacetime itself. Instead of assuming a smooth, continuous reality from the start, it proposes that at the tiniest possible scale, the Planck scale spacetime isn't smooth. It's a chaotic, jumbled froth. To build a universe out of this chaos, physicists begin with the simplest possible building blocks, tiny, four-dimensional triangular pieces called simplexes. Think of them as the elemental grains of spacetime. The process involves an astronomical number of these grains. The theory doesn't just arrange them randomly, it follows two crucial rules. The first is causality, meaning every piece must be connected in a way that preserves cause and effect. You can't have an effect happening before its cause, even in this jumbled quantum soup. The second rule is that the simulation is dynamic. The geometry is allowed to fluctuate and evolve according to the laws of quantum physics. Researchers run massive computer simulations, randomly connecting these trillions upon trillions of triangular blocks in every possible configuration that obeys the causal rule. And then they use the principles of quantum mechanics to calculate which configurations are the most probable. It's a bit like throwing a billion dice an infinite number of times to see which overall pattern emerges most often. What they find is nothing short of miraculous. From this incredibly large ensemble of random, jumbled connections between fundamentally simple, low-dimensional building blocks, our familiar four-dimensional universe spontaneously emerges. At the largest scales, the simulation consistently produces a smooth, classical spacetime with three spatial dimensions and one time dimension, exactly as we observe. But here's the truly astonishing part. When they zoom into the very smallest scales within the simulation, the dimensionality of the universe appears to change. At these ultra-microscopic levels, the effective dimension isn't 4, it drops down to 2. This suggests that the fundamental ingredients of reality might actually be two-dimensional, and that our perception of a four-dimensional world is a collective, large-scale illusion. A property that only emerges when you have a sufficient number of these simple pieces working together in concert. It's similar to how a single water molecule isn't wet and doesn't have a temperature or flow. It's just a molecule, but when you gather trillions of them together, the property of wetness and the behavior of a fluid emerge. In the same way, causal dynamical triangulation posits that dimensionality itself is an emergent property, a direct result of the way the quantum grains of spacetime interconnect on a cosmic scale. This offers a profound resolution to the problem of combining quantum mechanics with general relativity. The infamous singularities where physics breaks down, like at the center of a black hole or the moment of the Big Bang, might simply be places where this smooth, emergent geometry dissolves back into its more primitive, lower-dimensional components. We are not living in a universe with dimensions. We are living in a universe because of dimensions, a cosmic pattern that arose from the quantum noise. While string theory proposes that the fundamental ingredients of the universe are tiny vibrating strings, Another powerful and deeply elegant framework takes a completely different approach, asking not what exists within space and time, but what space and time themselves are made of. This is loop quantum gravity, or LQG, a theory that dares to quantize the very fabric of spacetime, painting a breathtaking picture of a universe woven from a cosmic web of relationships. For a century, Einstein's general relativity has described gravity not as a force, but as the curvature of a smooth, continuous spacetime, a four-dimensional stage that warps and bends in the presence of mass and energy. This picture works perfectly on large scales, but it completely breaks down at the center of black holes or at the moment of the Big Bang, where the mathematics predicts points of infinite density and temperature called singularities, places where the laws of physics simply stop making sense. These infinities are a clear signal that the classical theory of relativity is incomplete. Loop quantum gravity tackles this problem head-on by applying the rules of quantum mechanics not to matter moving in space, but to the geometry of space itself. The core idea is that spacetime is not smooth and continuous down to the smallest scales. Instead, it is granular or atomized, just as water, which appears perfectly smooth and fluid, is actually made of individual H2O molecules. The fabric of reality is composed of tiny, indivisible quanta of space. In LQG, the fundamental building blocks are one-dimensional loops of gravitational field. Picture an incredibly fine mesh, but instead of a rigid grid, think of it as a dynamic network of interconnected links. These loops aren't embedded in space, they literally define space. Where they intersect and link together, they create a volume. The area of a surface is determined by how many loops puncture it, and the volume of a region is determined by how they knot and weave together. This structure is formally known as a spin network, a mathematical graph where the links represent quantized areas and the nodes represent quantized volumes. The term spin comes from quantum mechanics, referring to the intrinsic angular momentum of particles, and it appears here because the mathematical language used to describe these networks is the same used to describe how particles like electrons behave. This provides a direct, profound bridge between the quantum world and the geometry of the cosmos. The spin network is not a static object, it is a dynamic entity that evolves over time. As it changes, the network describes not just space but spacetime. This evolving history is called a spin foam, a complex, frothing structure that represents all possible configurations of spacetime geometry. Much like the path of a particle is the sum of all its possible histories in quantum theory. Now, while loop quantum gravity is fundamentally a theory of our familiar three spatial dimensions plus time, its radical rethinking of geometry opens a fascinating door. Some of its most compelling results come from applying its principles to the very beginning of our universe. In the standard Big Bang model, we hit a singularity, a point of infinite density where everything began. But in loop quantum cosmology, which applies LQG's principles to the entire cosmos, that singularity doesn't exist. Instead of an infinitely dense point, the equations show that the gravitational pull of all that energy and matter actually creates a colossal repulsive force. This quantum pressure becomes so immense that it prevents the universe from collapsing to a point. Instead of a big bang, we get a big bounce. Our expanding universe could have been born from the collapse of a previous cosmic phase, rebounding into a new expansion, forever avoiding the dreaded singularity where physics fails. This granular, network-based view of reality also suggests a new way to think about connections to higher dimensions. A spin network itself exists in a somewhat abstract mathematical space. While it defines our three-dimensional world, the network's full structure could be seen as embedded in a higher dimensional space to help us visualize its complex connections. Much like a 3D model of a social network is projected onto a two-dimensional computer screen. More speculatively, the nodes and links of the spin network could represent portals or bridges to other dimensional structures. or perhaps the spin foam's evolution could generate effective, emergent higher dimensional behaviors on larger scales. This discrete, pixelated vision of the cosmos offers a powerful alternative to the extra dimensions of string theory, suggesting that the deepest secrets of quantum gravity may not be found in unseen dimensions, but in the intricate, quantum-connected threads from which the tapestry of our own universe is woven. From the granular, quantum-woven fabric of spacetime, we now turn to a theory that proposes a different kind of multiplicity, one born not from geometry but from possibility itself. This is the many worlds interpretation of quantum mechanics, a concept that transcends the idea of parallel universes and suggests they might be the natural consequence of a reality unfolding in a breathtakingly vast, abstract dimensional arena. To understand this, we must first grapple with the central weirdness of quantum mechanics. In the subatomic world, particles don't have definite properties until they are measured. An electron, for example, exists in a blurry state of superposition, meaning it could be spinning both clockwise and counterclockwise at the same time. It's only when a scientist makes an observation that this fuzzy cloud of potential seems to collapse into a single, definite outcome. The orthodox Copenhagen interpretation treats this collapse as a fundamental yet mysterious process. The many worlds interpretation proposed by Hugh Everett in 1957 eliminates the mystery of collapse with a radical and elegant solution. It simply never happens. Instead, every single possible outcome of a quantum event actually occurs, but each one plays out in a newly branched parallel universe. Now, the popular conception is of an infinite number of Earths, each with a slightly different version of you. But this is a vast oversimplification. Everett's mathematics suggest something far more profound. These aren't just universes out there somewhere in space. They are better understood as distinct, non-communicating branches of a single, universal quantum wave function. And this is where the concept of dimensionality takes a spectacular leap. The arena in which this infinite branching occurs is not our familiar four-dimensional spacetime. It is an abstract mathematical construct known as a Hilbert space. Think of Hilbert space as a cosmic canvas of potentially infinite dimensions, where each dimension doesn't represent a direction you can move in, like left or right, but rather represents a complete possible state of the entire universe. Every fundamental particle, every force, every configuration of matter is a point or a vector in this unimaginably high-dimensional space. The evolution of reality is the smooth, deterministic flow of this universal wave function through Hilbert space. When a quantum event occurs, say, that electron is measured, the wave function doesn't collapse. It simply enters a state where it is entangled with the observer. The single reality we experience is just one thread in a much larger tapestry. The entire system bifurcates, and the total wave function now encompasses two non-interacting branches, one where the observer sees a clockwise spin, and another, entirely separate branch where they see a counterclockwise spin. Both are equally real, both are encoded within the higher dimensional structure of the wave function, but they have decohered, meaning they can no longer influence or detect one another. In this breathtaking view, the many worlds are not separate physical places located in some hidden fifth dimension. They are different vibrational modes or configurations within this colossal Hilbert space. Every quantum decision, from the decay of a radioactive atom to a choice made in your brain, creates a new branch, adding another layer of complexity to this infinite dimensional landscape. The dimensions of Hilbert space are not curled up or warped. They are the fundamental axis of possibility itself, and our perceived reality is just a single, random walk through this eternal, branching tree of potential. This interpretation doesn't just add extra spatial dimensions to the universe. It suggests that the true, complete reality is a static, multidimensional mathematical object, and what we experience as the flow of time is merely our conscious journey along one specific path within it. Yet if the many worlds interpretation posits a reality branching through an abstract space of possibilities, the next theory takes this idea to its ultimate, perhaps most extreme, logical conclusion. It asserts that the universe isn't just describable by mathematics, it is mathematics. This is the mathematical universe hypothesis, a profound and provocative idea championed by cosmologist Max Tegmark. Tegmark begins with a simple but deep observation that has puzzled physicists and philosophers for centuries: the unreasonable effectiveness of mathematics in the natural sciences. Why is it that a set of abstract rules and symbols invented by the human mind can so perfectly predict the behavior of subatomic particles, the motion of planets, and the evolution of the cosmos? The traditional view is that mathematics is a language, a uniquely powerful tool we have discovered for describing an external physical reality. Tegmark turns this completely on its head. He proposes that the external physical reality is the mathematics. There is no separate, tangible universe out there that the math is describing. The mathematical structure itself is the universe. To grasp this, think of a video game. The world you experience on screen, the mountains, the characters, the weather, isn't made of atoms and molecules. It is made of code, of ones and zeros processed by a computer. The physics of that game world, like gravity or how objects collide, are just the logical outcomes of its underlying algorithms. Tegmark suggests our reality operates on the same principle, just with vastly more complex equations. An electron isn't a tiny ball of stuff, it is a solution to the Dirac equation. A gravitational field isn't a warping of a fabric, it is a manifestation of Einstein's field equations. In this view, all physical things are simply patterns and relationships within a mathematical structure. We aren't made of particles, we are self-aware patterns within a complex mathematical object. This leads to the hypothesis's staggering and most controversial implication. If our universe is a mathematical structure, what about all the other mathematical structures? Mathematics is not limited to the equations that happen to describe our particular cosmos. There are an infinite number of other self-consistent mathematical systems, some with different numbers of dimensions, different fundamental constants, and different physical laws. Tegmark's hypothesis states that all of these mathematically possible structures exist physically as well. They are all equally real. Our four-dimensional spacetime, governed by the Standard Model and general relativity, is just one specific mathematical set, one particular page in the infinite library of mathematical existence. This is where the concept of dimensionality explodes beyond comprehension. In this grand multiverse of mathematical structures, the idea of 3 dimensions of space and 1 of time is merely a local bylaw. Other mathematical universes could have 5, 10, or 500 spatial dimensions. Some might have multiple time dimensions, leading to realities where cause and effect become labyrinthine and unpredictable. Others might have no time dimension at all, existing as static, eternal mathematical forms. These aren't dimensions curled up within our space. They are entirely separate, self-contained mathematical realities with their own complete and independent dimensional frameworks. The reason we find ourselves in this particular universe, with its 3 spatial dimensions and life-friendly constants, is not because it's special, but simply because it's a structure complex enough to contain self-aware substructures like us, that can observe and ponder their own existence. This is the ultimate form of the anthropic principle, applied to the entire landscape of mathematical possibility. The mathematical universe hypothesis doesn't just suggest that hidden dimensions are possible. It declares that every conceivable form of dimensionality, every possible geometric and temporal arrangement that can be described without logical contradiction, must exist somewhere in the great ensemble of reality. It is a vision of a truly complete and absolute multiverse, where the only thing that is impossible is a mathematical contradiction. But to truly appreciate the elegance of this warped geometry, we need to understand the problem it was designed to solve, the hierarchy problem. This is the baffling, enormous disparity in strength between the fundamental forces. The strong nuclear force is 100 times stronger than the electromagnetic force, which is in turn 1,000 times stronger than the weak nuclear force. But then we come to gravity, and the numbers become almost absurd. Gravity is 10 to the 40 times weaker than the strong force. To put that into perspective, that's a 1 followed by 40 zeros. It's the difference in scale between a single proton and the entire observable universe. For decades, physicists assumed this weakness was an intrinsic, fundamental property of gravity itself, but it presented a major puzzle. Why would nature have such a wildly unbalanced set of forces? The Randall-Sundrum model offers a breathtakingly simple and beautiful alternative. Maybe gravity isn't inherently weak at all. Perhaps its fundamental strength is actually on par with the other forces, but its effects are dramatically diluted by the hidden geometry of a warped fifth dimension. Imagine two people trying to communicate across a massive curved valley. One person stands on a tall, sheer cliff, the Planck brane where gravity is born, and the other stands far below in the flatlands, our brane, the TV brane where we live. When the person on the cliff shouts, the sound waves have to travel across the vast, warped expanse of the valley. By the time they reach the listener in the flatlands, the sound is incredibly faint, reduced to a mere whisper. The shout itself was powerful, but the curved landscape sapped its strength during the journey. This is precisely how warping solves the hierarchy problem. The true, raw power of gravity is generated on the distant Planck brane, but the exponential warping of the space between the branes, often described by what's called the warp factor, acts like a cosmic muffler, suppressing gravity's influence by that colossal factor of 10 to the 40 by the time it reaches our brane. We only ever experience this faint echo, this diluted remnant of gravity's true might. This mechanism is so effective that it doesn't require the extra dimension to be microscopically small, like in the older Kaluza-Klein model. In the Randall-Sundrum setup, the fifth dimension can be large or even infinite in size, and yet remain completely hidden from our view because everything that makes up our world, all the particles of the standard model like electrons and quarks, are stuck or localized on our brane. We are like paintings on a canvas, able to move around within the two dimensions of the painting, but utterly oblivious to the vast gallery that stretches off into the distance. The only thing that can leak off our canvas and travel through the gallery is gravity, because it is the curvature of the bulk space itself. This incredible idea isn't just a mathematical curiosity. It makes real, testable predictions that could one day be verified. If gravity can propagate through the bulk, then it might be possible for us to create or detect objects that also access this higher dimensional space. Particle colliders like the Large Hadron Collider could potentially produce not just new particles, but miniature, higher dimensional black holes that would instantly evaporate in a shower of characteristic radiation. Alternatively, they could create exotic, massive vibrations of gravity known as Kaluza-Klein gravitons. These wouldn't be the massless gravitons of traditional theories, because they are tied to the warped geometry. They would have mass, and they would appear in our detectors as missing energy carried away into the bulk. Finding evidence of such events would be our first direct glimpse into the warped architecture of the cosmos, proving that the weakness of gravity is not a fundamental mystery, but a profound clue pointing toward the hidden, curved dimensions that shape our reality. Up until now, the brane world scenarios we've explored have presented a compelling picture. Our familiar particles of matter and force are trapped on our three-dimensional membrane, while only gravity is free to explore the higher dimensional bulk. But what if that's not the entire story? What if the walls of our dimensional prison are not so absolute? This brings us to a fascinating and radically different class of models known as universal extra dimensions, or UD. In this scenario, the extra dimensions are not a secret garden for gravity alone. They are, as the name implies, universal. Every single fundamental particle, every electron, every quark, every photon, is granted the freedom to propagate through the full higher dimensional space. There is no brane to trap them. The entire fabric of spacetime in all its dimensions is their playground. This might sound like a simple tweak, but its implications are nothing short of revolutionary, transforming our entire particle zoo and offering a crystal-clear path to experimental discovery. To understand how this works, we need to revisit the brilliant idea from Oscar Klein. In these models, the extra dimensions are still compactified, curled up into a tiny circle or other shape. When a particle moves through this higher dimensional realm, its motion isn't just forward and backward. It can also have momentum around this tiny, circular direction. From our perspective, stuck in our three large dimensions, we can't perceive this circular motion directly. Instead, we interpret it as part of the particle's mass. According to Einstein's famous equation, energy and mass are equivalent. The kinetic energy a particle gains from whizzing around the compactified dimension adds to its rest mass, making it appear heavier to us. This leads to one of the most dramatic predictions in all of physics. For every single fundamental particle we know of, there could be an entire tower of heavier, excited copies. These are known as Kaluza-Klein partners. Imagine an electron. In our three-dimensional world, it has a specific, well-known mass, but in a universe with a universal extra dimension, that same electron could exist in a state where it has 1 unit of momentum in the circular direction. This version would be absolutely identical to the standard electron in every way: same electric charge, same spin, same interactions, except it would be significantly heavier. There could be another copy with 2 units of momentum, heavier still, and so on, creating an infinite series of particles marching up the mass scale. This doesn't just apply to electrons, it applies to everything. There would be Kaluza-Klein photons, Kaluza-Klein quarks, Kaluza-Klein gluons, and Kaluza-Klein neutrinos. Each one a perfect mirror of its standard model counterpart, but with a mass that directly reveals the size and shape of the hidden dimension. The mass of the first-tier Kaluza-Klein partner is inversely proportional to the radius of the extra dimension. If the dimension is larger, these particles are lighter and easier to produce. If it is smaller, they are heavier and more difficult to access. This provides a spectacularly clear signature for scientists hunting for extra dimensions at particle accelerators like the Large Hadron Collider. Instead of searching for vague hints of missing energy or exotic gravitational effects, they can look for the direct production of these heavy twin particles. The process would be breathtakingly simple in principle. Smash protons together with enough energy, and if universal extra dimensions exist, you could literally create matter that has momentum in a hidden direction. These heavy partners would be unstable and would rapidly decay back down to the lightest standard model particles, emitting a telltale cascade of energy and other particles that would stand out in the detectors. What makes this signature particularly compelling is that these Kaluza-Klein particles wouldn't appear randomly. They would come in pairs, and their decay patterns would be governed by a new conserved quantity related to momentum in the extra dimension, often called Kaluza-Klein parity. This would ensure that the lightest Kaluza-Klein particle, often a partner of the photon or neutrino, could be stable. And if it's stable, neutral, and only interacts weakly, it would be a perfect candidate for the mysterious dark matter that holds galaxies together. In one elegant framework, universal extra dimensions could solve 2 of the universe's greatest puzzles, revealing the hidden architecture of space-time and identifying the invisible matter that makes up most of the cosmos. While string theory provides a beautiful mathematical framework for a universe of 10 or 11 dimensions, it also presents a staggering and, for some, deeply troubling implication. The theory doesn't yield one unique description of reality. Instead, it predicts a vast, perhaps infinite, array of possible realities. This is the concept of the string theory landscape, a cosmic archipelago of potential universes so enormous it challenges our very understanding of physics and our place in the cosmos. The root of this multiplicity lies in those 6 hidden dimensions curled up into Calabi-Yau shapes. The mathematics of string theory allows for an astronomical number of different ways these dimensions can be compactified. Each distinct configuration is like a different tuning of the cosmic instrument, and each tuning produces a different set of physical laws. The specific geometry of the curled-up dimensions determines the number of particle families, the masses of those particles, the strength of fundamental forces, and even the value of the cosmological constant, the energy density of empty space that drives the universe's expansion. Now, the number of possible stable configurations isn't just large, it is mind-numbingly, incomprehensibly vast. Estimates place the number at around 10 to the power of 500. That's a 1 followed by 500 zeros. To grasp the scale of this number, consider that the total number of atoms in the entire observable universe is estimated to be around 10 to the power of 80. The number of possible universes in the string landscape is exponentially larger than the number of atoms in our own. It is a number so colossal that every conceivable combination of physical constants, every possible version of the laws of physics, and every imaginable universe, no matter how bizarre or uninhabitable, is almost certainly represented somewhere in this landscape. This leads to a profound and controversial shift in perspective. In this view, our universe is not special or fine-tuned. It is simply one possible outcome among a practically infinite number of others. The fact that our constants seem perfectly calibrated for the emergence of stars, planets, and life is not evidence of a grand designer. It is a consequence of a staggering selection effect known as the anthropic principle. We find ourselves in this particular universe with its specific set of laws, simply because it is one of the extremely rare configurations that allows for our existence. We could not possibly observe a universe that didn't permit observers. The landscape, therefore, offers an explanation for the apparent fine-tuning of our cosmos without invoking a single, unique theory of everything. This idea is both liberating and, for many physicists, deeply unsettling. It suggests that the ultimate goal of physics, to find a single, elegant set of equations that uniquely predicts our universe, might be unattainable. Instead of a unique theory of everything, we may have a theory of anything, a framework that allows for every possible outcome. The hope that the laws of physics are inevitable and beautiful gives way to the possibility that they are, in a sense, accidental, a random draw from a cosmic lottery. The landscape casts our universe not as a necessary truth, but as a single possibility, one tiny island in an endless ocean of other realities, most of which would be utterly alien and unrecognizable to us. This incredible diversity of possible realities within the string landscape leads us directly to one of the most profound and debated ideas in modern cosmology, the anthropic principle. If there are 10 to the 500 different ways for a universe to be, why does ours have the specific properties it does, most notably, 3 expansive dimensions of space and 1 of time? The anthropic principle suggests a startlingly simple answer. We observe this particular dimensionality because it is a necessary prerequisite for our own existence. A universe with a different number of large spatial dimensions would likely be sterile, incapable of forming the complex structures like galaxies, stars, planets, and life that are required for anyone to be around to notice. The physics of other dimensions paints a clear picture of why 3 is the magic number. Let's start by imagining a 2-dimensional universe, a truly flat plane like a sheet of paper. In such a world, the laws of physics themselves become problematic. For instance, Newton's law of universal gravitation states that the force of gravity weakens with the square of the distance. In 3 dimensions, this creates stable orbits. Planets can gracefully circle stars for billions of years. But in a 2-dimensional world, gravity would weaken in direct proportion to the distance, a much gentler decline. This slight change has catastrophic consequences. It prevents the formation of stable, closed orbits. A planet trying to circle its star would either spiral inward and be consumed or drift away into the void, making solar systems and thus habitable planets impossible. The problems continue down to the microscopic scale. In a two-dimensional world, the wiring of complex life becomes a logical nightmare. Imagine a digestive tract. In our three-dimensional bodies, a tube can run from one end to the other, allowing for the one-way processing of food. In a truly two-dimensional creature, a digestive tract would literally split the animal in two, severing its body into two disconnected halves. Similarly, the intricate neural networks of a brain, with axons and dendrites weaving over and under one another, cannot exist without a third dimension to allow these connections to cross without interfering. Two-dimensionality seems to impose a fundamental simplicity that is incompatible with the complexity required for life as we know it. Now, what about a universe with more than 3 large spatial dimensions, 4, 5, or even more? This scenario is equally hostile to life, but for the opposite reason. Forces become too powerful. In higher dimensions, the fundamental forces like gravity and electromagnetism would weaken much more dramatically with distance. In 3 dimensions, if you double your distance from a star, its gravitational pull on you falls to a quarter. In 4 large spatial dimensions, it would fall to 1/8. In 5 dimensions to 1/16, and so on. This intense weakening sounds like it might make gravity even more feeble, but the opposite is true for the stability of matter itself. The real issue is with the structure of atoms, the building blocks of everything. An atom is a nucleus of protons and neutrons with electrons whizzing around it. In 3 dimensions, the electrical force that binds electrons to the nucleus allows for stable, well-defined electron orbitals, the famous s, p, d, and f shells that govern chemistry. In a universe with 4 or more large spatial dimensions, the equations that describe these orbitals have no stable solutions. Electrons could not maintain stable orbits. They would either spiral into the nucleus or fly off into space. Atoms, and therefore molecules, chemistry, and solid matter, simply could not exist. There would be no planets, no water, no DNA, just a formless, chaotic soup of particles unable to bind together. Therefore, the very fact that we are here to ponder the nature of our universe acts as a powerful filter. We do not observe a universe with 2 large dimensions because it cannot support solar systems or complex organisms. We do not observe a universe with 4 or more large dimensions because it cannot support atoms or chemistry. We observe exactly 3 large spatial dimensions and 1 time dimension because this specific configuration is, as far as we can tell, the only one that allows for the long-term stability of galaxies, the nuclear fusion in stars, the formation of rocky planets, and the incredibly complex molecular machinery that constitutes life. Our existence as observers selects for this particular dimensional arrangement out of the vast landscape of possibilities. It is not that the universe was designed for us, but rather that we are a product of a universe that accidentally stumbled upon a set of physical laws, including its dimensionality, that permitted our evolution. We are a cosmic coincidence, living in a rare universe where the architecture of reality itself is just right for story to unfold. Now we arrive at a theory that challenges the most basic assumption of all, that dimensions are whole numbers. We've always spoken of 3 dimensions of space, or 10 or 11. But what if the very fabric of spacetime defies this neat categorization? What if dimensionality itself is not an integer but a fraction? This is the astonishing proposal of fractal spacetime, a concept that suggests the universe is built on a geometry of endless, self-similar complexity. To grasp this, we need to understand what a fractal is. Picture a coastline from a satellite. It has a certain length, but as you zoom in, you see bays and peninsulas adding more detail and length. Zoom in further, and you see individual rocks, then grains of sand. At every scale, the structure is similarly complex, and the measured length depends entirely on your ruler. A fractal has a fractional dimension, a mathematical measure of its complexity that lies between the whole numbers we're used to. A very crinkly coastline might have a dimension of 1, 2, more than a simple line dimension 1, but less than a full plane dimension 2. The application of this idea to physics is truly revolutionary. It suggests that spacetime itself might not be smooth and continuous, nor simply granular, but fractal in its very nature. At the incredibly small scale of the quantum foam, where spacetime is believed to churn with violent fluctuations, the concept of a clear, definable distance may break down. The path of a particle moving through this foam wouldn't be a smooth line. It would be a wildly zigzagging, crinkled path, so complex that its effective dimension could be something like 1, 3 or 1, 7. In this view, the three-dimensional space we experience in our everyday lives is not the fundamental reality. It is an average, a large-scale illusion that emerges from the collective behavior of a vast network of fractal connections at the smallest scales. This has a direct and profound implication for one of the universe's greatest mysteries, the nature of gravity. Quantum gravity has been the holy grail of physics because the smooth geometry of Einstein's general relativity is incompatible with the chaotic, probabilistic world of quantum mechanics. But if spacetime has a fractal structure at the quantum level, it could provide a natural meeting point. The fractal properties could act as a built-in regulator, smoothing out the wild fluctuations and infinities that normally plague attempts to quantize gravity. The dimension of spacetime wouldn't be fixed at 4. It could vary with the energy scale or the size of the region you're probing. At very high energies near the Big Bang or at the center of a black hole, the dimension might flow to a lower value, perhaps even 2, preventing the formation of a true singularity where physics breaks down. This fractal geometry wouldn't just be a feature of space. Time itself could possess a fractional dimension, fundamentally altering our understanding of cause, effect, and the very arrow of time. The evidence for this mind-bending idea might not be locked away in a distant particle accelerator. It could be written across the largest structures in the cosmos. Astronomers mapping the universe have found that galaxies are not scattered randomly. They are arranged in an immense cosmic web, a vast network of filaments and clusters surrounding enormous voids. This large-scale structure is not smooth or uniform. When scientists analyze its geometry, they find it possesses a faint but detectable fractal-like quality over certain scales. It is a structure of astonishing complexity, and some physicists speculate this could be a fossilized imprint of the universe's primordial fractal nature, a ghostly echo from its earliest moments when spacetime itself was seething with fractional dimensions. This theory invites us to see the universe not as a stage with a fixed number of dimensions, but as a dynamic, evolving fractal, where the very concept of dimension becomes a fluid and scale-dependent property, weaving together the quantum and the cosmic into a single, breathtaking tapestry of infinite complexity. We've explored how dimensions might be hidden, how they might be warped, and how our universe could be a membrane floating in a higher dimensional space. But now, we venture into perhaps the most elegant and profound connection between the very large and the very small, a theory that proposes a breathtaking bridge between the two great pillars of modern physics, general relativity and quantum mechanics. This is the ER equals EPR conjecture, a deceptively simple equation that suggests the spooky quantum connection between entangled particles is in fact a physical wormhole threading through the cosmos. To appreciate this radical idea, we need to understand its two halves. ER stands for Einstein-Rosen bridge, the formal name for a wormhole. In 1935, Albert Einstein and his colleague Nathan Rosen found a solution to the equations of general relativity that described a tunnel or bridge connecting two separate points in spacetime. Think of it as a cosmic shortcut, a way to potentially travel from one galaxy to another without crossing the immense distance between them. For decades, these wormholes were considered mathematical curiosities, as they seemed to be unstable and would snap shut instantly if any matter tried to pass through. In that very same year, 1935, Einstein published another paper with Boris Podolsky and Nathan Rosen, the EPR paper. This one targeted quantum mechanics, highlighting its most bizarre feature, entanglement. They described a thought experiment where two particles become linked or entangled. Once connected, measuring the property of one particle, say, its spin instantly determines the property of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, as it seemed to violate the universal speed limit set by light, and it deeply troubled him. For most of the 20th century, these two 1935 papers were seen as separate critiques from Einstein, one about strange spacetime geometries, the other about the absurdity of quantum weirdness. They lived in different worlds, but in 2013, physicists Juan Maldacena and Leonard Susskind made a spectacular leap. They proposed that these two concepts aren't just related, they are two different descriptions of the same underlying reality. ER equals EPR. An Einstein-Rosen bridge is the same thing as an EPR pair of entangled particles. Let's unpack what this actually means. Imagine two entangled particles, one here on Earth and another on a planet in a distant galaxy. Quantum mechanics says they are instantly connected, but it doesn't say how. The ER equals EPR conjecture provides a stunningly geometric answer. They are connected by a microscopic wormhole. This isn't a tunnel through our familiar three dimensions. It is a shortcut through the higher dimensional bulk, the space outside our brain that we discussed in theories like Randall Sundrum. The quantum link, that spooky action, isn't action at a distance at all. It is action through a shortcut, a geometric connection that makes the two particles, no matter how far apart they seem in our three-dimensional space, immediate neighbors through a hidden extra dimension. This turns our understanding of entanglement completely on its head. The bizarre, non-local connection that so troubled Einstein is recast as a local connection. It just happens to be a connection that travels through a dimension we cannot perceive. The information isn't teleporting magically across space. It is taking a geometric detour through the bulk. This wormhole, or ER bridge, is not a traversable tunnel for spaceships. It is incredibly tiny, likely existing at the Planck scale, and it acts as a perfect channel for quantum information to flow. The implications of this idea are staggering, as it suggests that the fabric of spacetime itself might be woven from quantum entanglement. Think of the universe as a vast, intricate network. Each pair of entangled particles is connected by one of these microscopic wormholes. Now, imagine a complex web of trillions upon trillions of entanglements. According to this conjecture, this web of quantum connections could literally stitch together the geometry of spacetime. Space isn't just empty nothingness. It is a dense, dynamic tapestry of quantum links, each one a tiny thread in the cosmic fabric. This provides a potential pathway to unified general relativity, which describes the geometry of spacetime, with quantum mechanics, which describes the behavior of particles. They are not separate theories. One might be the manifestation of the other. The force of gravity and the curvature of spacetime could emerge from the quantum entanglement between particles. This perspective also offers a fresh way to look at black holes. The ER equals EPR conjecture was partly inspired by the black hole information paradox. If two black holes become entangled, the conjecture suggests they would be connected by a giant wormhole, a scenario that aligns perfectly with the predictions of general relativity. This geometric picture helps resolve the paradox by showing how information that falls into a black hole might not be lost forever, but preserved in its entanglement connections with the rest of the universe. The conjecture paints a universe where the deepest layers of reality are not particles or waves, but connections. a cosmic network where quantum links and geometric shortcuts are one and the same, revealing a hidden unity at the heart of physics. This intricate dance between quantum fields and hidden geometry brings us to a cornerstone concept that not only stabilizes these extra dimensions but could also reveal them: supersymmetry. Often discussed for its potential to solve the hierarchy problem and provide candidates for dark matter, supersymmetry shares a far deeper, more fundamental bond with the idea of higher dimensional spaces, especially within the framework of superstring theory. At its heart, supersymmetry, or SUSY, proposes a profound and elegant symmetry of nature. For every known type of particle with a half-integer spin, called a fermion, there should exist a partner particle with an integer spin, called a boson, and vice versa. This means the electrons and quarks that make up our atoms would have superpartners named selectrons and squarks, while force-carrying particles like photons and gluons would have partners called photinos and gluinos. This pairing isn't just a way to double the particle count. It's a mathematical transformation that beautifully links matter particles, the fermions, with force particles, the bosons. The connection to extra dimensions is not incidental, it is absolutely essential. Superstring theory, as we've discussed, only works consistently in 10 dimensions. But for the theory to be stable and free of mathematical inconsistencies known as anomalies, it requires supersymmetry to be woven into its very fabric. This is why it's called superstring theory. Supersymmetry acts as a cosmic regulatory force for those 6 hidden, curled-up dimensions. Without it, the quantum fluctuations and corrections within these tiny Calabi-Yau shapes would be uncontrollable. They would generate enormous, untenable energy densities that would cause the extra dimensions to either collapse in on themselves or expand uncontrollably, violently destabilizing the very fabric of spacetime. Supersymmetry's precise cancellations between fermionic and bosonic contributions act as a balancing mechanism, taming these wild quantum effects and allowing the extra dimensions to settle into a stable, physical configuration. It is the mathematical glue that holds the compactified geometry together, making our universe with its specific physical laws even possible. This deep interplay means that the search for supersymmetry is about far more than just finding new particles. It is an indirect but powerful probe into the existence of these hidden dimensional architectures. If supersymmetry is discovered at a particle collider like the Large Hadron Collider, it won't just confirm a symmetry, it will provide the strongest evidence yet that the framework requiring extra dimensions superstring theory is on the right track. The properties of the superpartners we might discover, their masses and how they interact, would act as a unique fingerprint. This data could point physicists toward the specific way the extra dimensions are curled up, effectively allowing us to reverse engineer the geometry of the hidden universe from the particles we can observe in our 3-dimensional brain. Finding a selectron or a photino would be like finding a piece of a puzzle that was manufactured in a higher dimensional factory. Its very existence and characteristics would whisper secrets about the shape and size of the dimensions from which it originated, offering us an incredible glimpse into the complete, multidimensional nature of reality. Yet this incredible force of destruction presents a puzzle so profound that it has divided physicists for decades, challenging the very foundations of quantum mechanics. This is the black hole information paradox, and its potential resolution may lie not within the black hole's dark heart, but in the hidden architecture of the cosmos itself. The problem starts with a fundamental tenet of quantum physics: information cannot be destroyed. The universe is, in a sense, a vast computer that never loses a single bit of data. Every particle, every interaction can be described by a quantum wave function, and the evolution of that wave function is always reversible in principle. If you could somehow rewind the tape of the universe, you could trace every particle back to its origin, but black holes seem to shatter this principle. Imagine you have a book, a complete set of information, say the complete works of Shakespeare. You throw it into a black hole. according to classical general relativity, the book is gone forever, pulled inexorably toward the singularity at the center, where it is crushed out of existence. All that remains is the black hole itself, which is described by just three properties: its mass, its electric charge, and its spin. The intricate information contained in the sonnets, the characters, the very words themselves, appears to have been completely erased from the universe. This is a direct violation of quantum unitarity, the law that says information must be preserved. The plot thickened with Stephen Hawking's discovery that black holes aren't entirely black. Due to quantum effects near the event horizon, they slowly evaporate, emitting a faint glow of radiation. This Hawking radiation, however, poses an even greater problem. Hawking showed that this radiation is purely thermal. It is random noise like the heat from a stove and contains no information whatsoever about what fell in. After eons, the black hole will evaporate completely, leaving behind nothing but this featureless thermal radiation. The information about the book and everything else that ever fell in is seemingly lost forever. The universe's hard drive has been irreversibly wiped. So where could the information have gone? This is where the concept of hidden dimensions offers a breathtaking escape route. One of the most compelling solutions is a direct application of the holographic principle we discussed earlier. It posits that the information is never actually lost inside the black hole because it never actually falls in. Instead, when an object crosses the event horizon, all of its information is immediately and perfectly encoded onto the two-dimensional surface of that horizon. It's like a cosmic bit of data being written to a vast spherical hard drive. The three-dimensional object is gone from our perspective, but its complete description remains painted on the boundary. This preserves the information, satisfying quantum mechanics, while also respecting the classical view that nothing escapes the black hole. The information is saved, but it's stored in a scrambled, holographic form on a higher dimensional surface we cannot see. Another extraordinary possibility emerges from brane world scenarios. If our universe is a three-dimensional membrane floating in a higher dimensional bulk, then a black hole in our world might have a profound connection to this larger space. Some theories suggest that the information isn't stored on the horizon at all. Instead, it might leak out not into our universe but into the extra dimensions of the bulk. The singularity at the center of a black hole could act as a bridge or a portal to another brane or another part of the higher dimensional geometry. The information from our Shakespeare book wouldn't be destroyed. It would simply be translated into another reality, a parallel universe where the story continues to exist, just in a different dimensional language. From our confined perspective on our brain, the information is gone. But from a God's eye view of the full multidimensional cosmos, every single bit is perfectly preserved. This interplay between quantum mechanics and gravity, mediated by the idea of extra dimensions, suggests that the information paradox forces us to choose between two deeply held beliefs. Either information is truly lost, which requires a radical rewriting of quantum theory, or our understanding of locality. The idea that objects are only influenced by their immediate surroundings is incomplete. The holographic and brane world solutions powerfully argue for the latter. They suggest that the fabric of reality is woven with threads that connect points through hidden dimensions, making a mockery of our everyday notions of distance and separation. The preservation of information might be a non-local process happening across dimensions we are only beginning to mathematically conceive. The black hole, the ultimate destroyer, might ultimately be the key that unlocks the true multidimensional nature of the cosmos, showing us that information is the most indestructible substance in the universe. For decades, one of the most compelling mysteries in cosmology has been the nature of dark matter. We know it's there. Its gravitational pull is the only thing stopping galaxies from flying apart, but we have no idea what it's made of. Among the many theoretical candidates proposed, one class of particle has stood out as a particularly elegant solution: weakly interacting massive particles, or WIMP. These hypothetical particles are massive enough to form the gravitational scaffolding of the cosmos, yet they interact so weakly with normal matter that they simply pass through us and our detectors unseen. For years, the WIMP miracle was the guiding hope of dark matter searchers. This wasn't just a random guess, it was a prediction that emerged beautifully from supersymmetry, suggesting a particle with just the right mass and interaction strength to be produced in the early universe in exactly the abundance we observe for dark matter today. But what if this cosmic coincidence has an even deeper origin, one that ties directly into the architecture of hidden dimensions? This is where the concept of universal extra dimensions provides a stunning and independent pathway to the same profound conclusion. In these models, where every standard model particle can access the bulk, we saw how each one acquires a tower of heavier Kaluza-Klein partner particles. Now, these models often possess a powerful built-in symmetry. This symmetry, often called Kaluza-Klein parity, acts as a conservation law. It ensures that the lightest of all these Kaluza-Klein particles, often abbreviated as the LKP, must be completely stable. It cannot decay into any lighter standard model particles because that would violate this fundamental rule. It is, in essence, a fossil relic from the early universe, left over from the moment the extra dimensions first took their compactified shape. In many universal extra dimension scenarios, the prime candidate for this stable, lightest Kaluza-Klein particle is the first excitation of the photon, often called the Kaluza-Klein photon, or B1. Think of it as the heavy, unseen twin of the familiar particle of light. This particle is electrically neutral, which means it doesn't feel the electromagnetic force and won't interact with light or charged matter. Its mass would be determined by the size of the extra dimension, and for dimensions large enough to be probed by modern colliders, this mass would fall squarely in the range of hundreds of giga-electronvolts, making it truly massive on the particle physics scale. Most importantly, it would interact with ordinary matter only through the weak nuclear force and gravity, making it incredibly difficult to detect. It would literally just pass through the Earth as if it weren't even there. This profile should sound incredibly familiar. A massive, stable, neutral particle that interacts only weakly. That is the textbook definition of a WIMP. The universal extra dimension framework doesn't just hope for a WIMP. It predicts one as a fundamental consequence of its geometry. The WIMP miracle finds a second, independent, and perhaps more compelling origin story. It emerges not from supersymmetry, but from the very existence of an extra, compactified dimension of space. The dark matter that holds our galaxy together wouldn't just be some exotic particle. It would be literal evidence of momentum in a hidden direction, a particle that is massive because it is whizzing around a tiny, circular dimension we cannot perceive. This provides an electrifying motivation for the search for extra dimensions. Finding this Kaluza-Klein photon wouldn't just win a Nobel Prize for discovering dark matter. It would provide incontrovertible proof that our universe is fundamentally higher dimensional. The properties of this particle would be a direct message from the geometry of the hidden dimension. Its mass would tell us the precise size of the extra dimension, and its interaction rates could even hint at the shape. We would move from simply wondering if extra dimensions exist to precisely measuring their properties, using dark matter not just as a cosmic placeholder, but as the most precise tool in our kit for unraveling the true, multidimensional nature of reality. But all of these theories, from the holographic principle to the quantum foam, rely on a fundamental assumption: that gravity is a force woven into the fabric of spacetime itself. Yet, the other three fundamental forces, electromagnetism and the strong and weak nuclear forces, are all understood to be mediated by force-carrying particles. The photon carries the electromagnetic force, gluons carry the strong force, and the W and Z bosons carry the weak force. So, what about gravity? For a complete and unified picture of the cosmos, physicists have long predicted the existence of its own messenger particle, the graviton. This elusive, hypothetical particle is the final and most crucial piece in the quantum puzzle, and its very nature is inextricably linked to the number of dimensions in our universe. In the quantum world, forces aren't action at a distance, they are the result of particles exchanging these force carriers. Think of two people standing on a frictionless ice rink, tossing a heavy ball back and forth. With each throw and catch, they are pushed further apart. The exchange of the ball mediates a repulsive force between them. Now, imagine two stars orbiting each other. In the quantum picture, they are constantly exchanging a vast number of gravitons, and it is this exchange that creates the attractive force of gravity we observe. The graviton would be massless like the photon, and it would travel at the speed of light, perfectly matching the long-range, never-ending pull of gravity described by Einstein. Here's where the number of dimensions becomes absolutely critical. The properties of a force-carrying particle are defined by its spin, and this spin dictates how many different polarization states it can have, essentially, the different ways it can wiggle or orient itself in space. In our familiar four-dimensional universe, the graviton must have a spin of 2, which gives it exactly 2 polarization states. This is a fixed mathematical requirement. But if the universe has more than 3 spatial dimensions, this requirement changes dramatically. In a higher dimensional bulk, the graviton would have more ways to wiggle. In a world with 5 total dimensions, it would have 5 polarization states. In a world with 10 or 11 dimensions, it would have even more. The graviton's identity is not fixed. It is a direct reflection of the dimensional architecture it calls home. This change in the graviton's fundamental character has a direct and observable consequence. It alters the very law of gravity itself. Sir Isaac Newton taught us that the force of gravity weakens with the square of the distance. This inverse square law is why Earth's gravitational pull on the International Space Station is much weaker than its pull on you standing on the surface. But this law is a direct consequence of living in a universe with exactly 3 spatial dimensions. Gravity, like all forces, spreads out as it travels. In 3 dimensions, it spreads out over the surface area of an ever-expanding sphere, which grows as the distance squared. If there were a 4th large spatial dimension, gravity would spread out into that extra volume. The surface area of its sphere of influence would grow much faster with the distance cubed. This would cause the gravitational force to weaken much more rapidly with distance. For a universe with n spatial dimensions, the force of gravity weakens with the distance to the power of n1. This is the key to understanding how the graviton could provide our first direct proof of hidden dimensions. In scenarios like the large extra dimensions model, the graviton isn't just a particle that exists in the bulk, it is compelled to travel through it. While particles of matter like electrons and quarks might be stuck on our brane, the graviton, as the carrier of spacetime's geometry, can freely propagate through all dimensions. From our perspective on the brane, this means that some of the gravitons we emit could literally leak away into these unseen dimensions, taking their energy with them. This leakage would manifest as a subtle but detectable deviation from Newton's inverse square law at very small distances. If you could measure the gravitational pull between 2 objects with incredible precision as they were brought closer together, you might find that at sub-millimeter scales, gravity becomes just a tiny bit stronger than expected. This is because you're getting so close that a significant portion of the gravitational force hasn't had a chance to leak away into the extra dimensions yet. It's like having a leak in a hose. The further the water has to travel, the more it seeps out and the less pressure you have at the end. This incredible possibility has launched a new frontier in experimental physics. Teams around the world are conducting exquisitely sensitive tabletop experiments using precisely engineered pendulums, torsion balances, and micromechanical oscillators to measure the gravitational force between objects at distances smaller than the width of a human hair. They are literally hunting for the ghostly footprint of the graviton's journey into higher dimensions. Simultaneously, massive particle colliders like the Large Hadron Collider are searching for a different signature. If these extra dimensions exist and are large enough, the collider could actually produce real gravitons. But because gravitons interact so weakly, they would escape the detector completely unseen, leaving behind a telltale signature of missing energy and momentum, a clear imbalance in the accounting of a collision event that would scream the existence of an invisible particle carrying energy away into another dimension. The search for the graviton is therefore a two-pronged assault on the unknown, probing both the infinitesimally small and the incredibly energetic, all in pursuit of the particle whose very being would reveal the full, hidden dimensionality of our reality. While the search for gravitons and Kaluza-Klein particles points toward grand, energetic discoveries, one of the most sensitive tests for hidden dimensions is happening on an almost unimaginably small and quiet scale, using nothing more than the restless energy of empty space itself. This brings us to the Casimir effect, a subtle quantum phenomenon that transforms the void into a powerful laboratory for probing the very architecture of reality. To understand how it works, we first need to reimagine what we mean by nothing. In classical physics, a perfect vacuum is just empty space, a complete absence of anything. But quantum mechanics reveals this to be an illusion. What we call a vacuum is actually a seething, bubbling sea of quantum activity. Due to the Heisenberg uncertainty principle, pairs of virtual particles and their antiparticles are constantly flickering into and out of existence, borrowing energy from the vacuum for an immeasurably short time before annihilating each other and paying the energy back. This endless dance of creation and destruction means that even the emptiest space is filled with a foam of quantum fluctuations, and these fluctuations carry energy, a background hum of the universe known as zero-point energy. Now imagine placing two perfectly smooth, uncharged parallel metal plates extremely close together in this vacuum, separated by a gap mere nanometers wide. This setup, first proposed by Dutch physicist Hendrik Casimir in 1948, creates a fascinating constraint. Those quantum fluctuations aren't just random noise, they are waves, and like any waves, they can only exist at certain resonant frequencies. Outside the plates in the open vacuum, fluctuations of all possible wavelengths can exist, but in the narrow gap between the plates, only those fluctuations whose wavelengths fit perfectly between them are allowed. Think of it like the sound waves between two closely spaced walls. Only certain musical notes would resonate in that space. This means there are fewer possible quantum fluctuations between the plates than there are outside them. With more activity pushing on the outer surfaces of the plates than on the inner surfaces, the result is a tiny but measurable net force pushing the plates together. This is the Casimir effect, a mysterious, attractive force between two neutral objects, generated purely by the pressure difference in the quantum foam of empty space. This effect might seem like a microscopic curiosity, but it becomes a profound test for extra dimensions when we consider how those hidden realms would influence the quantum vacuum. If there are additional large spatial dimensions, as proposed in theories like the AD model, then the quantum fluctuations that make up the vacuum aren't limited to our familiar three dimensions. They, like the graviton, would be free to propagate into the full, higher dimensional bulk. The vacuum would have more room to fluctuate. This would fundamentally alter the spectrum of possible virtual particles, changing the very nature of the zero-point energy. Crucially, it would modify the precise calculation of how many fluctuations are allowed between the Casimir plates versus outside them. The presence of extra dimensions would effectively provide an additional outlet for the vacuum energy, subtly changing the strength of the attractive force predicted between the plates. This turns a delicate laboratory experiment into a powerful cosmic constraint. By measuring the Casimir force with exquisitely high precision, using advanced instruments like atomic force microscopes, and comparing the result to the theoretical prediction for a three-dimensional universe, physicists can effectively hunt for discrepancies. If the measured force is even slightly weaker or stronger than expected, it could be a signature that some of the vacuum's energy is bleeding away into dimensions we cannot see. The incredible sensitivity of these experiments allows them to probe for extra dimensions vastly smaller than those accessible to particle colliders. While the Large Hadron Collider might probe for dimensions as small as 10 to the minus 19 meters, precision Casimir force measurements can place stringent limits on the existence of extra dimensions up to several micrometers in size. They have effectively ruled out the possibility of large extra dimensions down to this scale, putting intense pressure on certain versions of the brane world hypothesis and forcing theorists to refine their models. It is a breathtaking thought. By measuring the invisible quantum pressure between two tiny plates, we are conducting a direct test on the fundamental dimensional structure of the entire cosmos, using the silent hum of nothingness itself as our guide. But our exploration of hidden dimensions isn't just about the forces and particles we know. It's also about the potential to create entirely new kinds of cosmic architecture. To understand this, we need to journey back to the universe's earliest, most violent moments. Picture the newborn cosmos, a seething plasma of unimaginable energy and heat. In this frenetic chaos, the fundamental forces and the very structure of spacetime itself were not yet fixed. As the universe expanded and cooled, it underwent a series of profound phase transitions, much like steam condensing into water or water freezing into ice. These transitions didn't happen smoothly everywhere at once. Different regions of space cooled at slightly different rates, and when their new, stable phases met, the mismatch could create persistent defects frozen into the fabric of reality. We see a simple version of this in everyday life. When water freezes into ice on a pond, the ice doesn't form a single, perfect crystal. Different patches of ice crystals form independently, and when they meet, their misaligned structures create fissures and fault lines, cracks in the ice. These cracks are topological defects, and the early universe is thought to have undergone similar processes on a cosmic scale, potentially creating three types of defects: domain walls, magnetic monopoles, and the most relevant for our story, cosmic strings. These aren't strings like in string theory. They are incredibly thin but immensely dense, filaments of energy, truly one-dimensional objects where the fundamental fields are trapped in a false, high-energy state. A cosmic string would be thinner than a proton, but with the mass of a mountain range crammed into every mile of its length. Now, here's the crucial connection to our topic. What if the phase transition that spawned these cosmic strings wasn't just about the familiar forces of our four-dimensional world? What if it was directly related to the process of compactifying and stabilizing the extra dimensions proposed by string theory? In the fiery forge of the Big Bang, the extra dimensions wouldn't have been neatly curled up. They, too, would have been unstable and fluctuating wildly. As the universe cooled, a critical phase transition would have occurred, forcing these extra dimensions to collapse down into their stable, compactified Calabi-Yau shapes. This process, known as dynamical compactification, would not have been perfectly uniform. Just like the ice on a pond, different regions of space might have settled on slightly different ways to curl up those extra dimensions. Where these different compactification regions met, the mismatch could have been sealed into a persistent flaw in spacetime, a cosmic string. This string would be a relic, a scar from the moment the higher dimensional nature of the universe was frozen into its current state. It would be a place where the extra dimensions are pinched or trapped in a different configuration, a fossilized reminder of a more symmetric, higher dimensional past. These strings, if they exist, would have been stretched to astronomical lengths by the universe's inflation, potentially forming a network of loops and infinite filaments that crisscross the entire cosmos. While we haven't definitively found one yet, their potential signatures are clear and dramatic. Their immense mass would warp space-time around them incredibly sharply, acting as ultra-powerful gravitational lenses. A cosmic string passing between us and a distant galaxy would not create a single distorted image, but would instead create a perfectly identical double image of that galaxy, a telltale sign of its unique wire-like geometry. Even more exciting is their connection to gravitational waves. A vibrating loop of cosmic string would be a powerful and persistent source of ripples in space-time, emitting a continuous hum of gravitational waves at a very specific frequency. As these loops lose energy through this radiation, they shrink and their hum shifts in pitch. The upcoming Laser Interferometer Space Antenna, or LISA, mission is designed to listen for these precise gravitational wave backgrounds. Finding a symphony of signals that matches the predicted decay of a network of cosmic strings would be spectacular, indirect evidence that our universe did indeed undergo a higher dimensional phase transition, locking away its extra dimensions and leaving these incredibly dense, one-dimensional scars as the only permanent record. But as our journey through the landscape of possibilities continues, a profound question emerges from this incredible diversity. With so many potential universes on the table, how do we separate the physically real from the mathematically possible? How do we know which of these 10 to the 500 vacua actually describe a universe that could truly exist, consistent with the deepest principles of quantum gravity? This is the critical mission of the swampland conjecture, a set of bold ideas that acts as a cosmic bouncer, deciding which theories get into the exclusive club of quantum gravity and which are left out in the cold. The term itself paints a vivid picture. The landscape is the vast but well-defined set of effective field theories, the mathematical descriptions of particles and forces, that can be successfully embedded into a complete theory of quantum gravity like string theory. These are the theories that could potentially describe a real, self-consistent universe. The swampland, in stark contrast, is the even vaster wilderness of seemingly consistent effective field theories that, despite their mathematical elegance, simply cannot be connected to a full quantum theory of gravity. They are dead ends, beautiful ideas that are ultimately incompatible with the deepest laws of physics. The swampland conjectures are the rules that help us tell the two apart, and they often place surprisingly strict limits on the very nature of dimensionality and the physics it allows. One of the most influential of these conjectures directly tackles the idea of stable, large extra dimensions. It's known as the distance conjecture. Imagine a scalar field, a kind of cosmic slider that could, in principle, change the size or shape of a compactified dimension. The distance conjecture states that as you try to move this field over a large range, effectively trying to make a compactified dimension become large and macroscopic, an entire tower of new particles predicted by string theory will suddenly become incredibly light and enter the physics of our world. Their appearance signals a complete breakdown of our effective field theory description. In practical terms, this means you cannot have a stable, large extra dimension without the entire physics of our universe being completely overthrown by a deluge of new, lightweight states. This conjecture provides a powerful argument for why the extra dimensions of string theory must remain compactified and tiny, forever hidden from our direct perception. It's not just a convenience, it's a fundamental requirement for a stable, predictable universe like our own. Another crucial swampland rule is the de Sitter conjecture, which casts a skeptical eye on one of the most important discoveries in modern cosmology, dark energy. Our universe appears to have a small, positive cosmological constant, which means empty space has a tiny amount of energy causing the expansion of the universe to accelerate. This state is described by a de Sitter space. However, many string theorists have found it incredibly difficult, if not impossible, to construct a stable de Sitter vacuum from string theory's fundamental ingredients. The de Sitter conjecture boldly states that such long-lived metastable states with a positive cosmological constant might actually be in the swampland. They might be mathematically possible in a simplified effective theory, but forbidden in a true theory of quantum gravity. If this conjecture holds, it would mean our current understanding of dark energy is incomplete, and its true nature must be something more dynamic, like a slowly evolving quintessence field that will eventually decay. This isn't just an academic debate. It strikes at the heart of the ultimate fate of our entire cosmos, suggesting that the accelerated expansion we see today may be a temporary phase on a much larger cosmic timescale. These conjectures transform the search for a theory of everything from a purely mathematical exercise into a process guided by physical principles. They act as a reality check, using the hard-won insights from string theory and quantum gravity to rule out entire classes of models that, while mathematically attractive, lead to logical inconsistencies or physical impossibilities. For researchers, navigating the swampland is like using a compass in a vast wilderness of equations. The conjectures point toward the regions where true physics resides and away from the treacherous bogs of beautiful but ultimately barren ideas. By imposing these strict constraints on what is possible, particularly regarding the size and stability of dimensions, the Swampland program suggests that the architecture of our universe is not an arbitrary selection from an infinite menu. It is a very specific and perhaps highly constrained solution, one where the number of large dimensions and the laws that govern them are not accidental, but are deeply intertwined with the most fundamental requirements for a coherent and stable reality. But if the idea of a universe woven from quantum threads or cosmic strings seems abstract, prepare yourself for a theory that challenges the very mathematical language we use to describe reality. What if the coordinates of spacetime themselves are not the reliable, fixed markers we believe them to be? This is the radical proposal of non-commutative geometry, a profound reimagining of the fabric of the cosmos where the very concept of a point in space and time dissolves into a fuzzy, quantum uncertainty. In our everyday world and in all of classical and quantum physics up until now, we assume that geometry is commutative. Let's break down what that means. Imagine you're giving someone directions to a treasure. You tell them to walk 5 steps north, then 3 steps east. They will end up at the exact same spot as if they had first walked 3 steps east and then 5 steps north. The order of your operations doesn't matter, the coordinates commute. This common sense rule is the foundation of all the mathematics we use to describe reality. But what if, at the very smallest possible scale, the Planck scale, this fundamental rule breaks down? What if telling someone to go north then east lands them in a completely different location than east then north? This is the core of non-commutative geometry pioneered by the French mathematician Alain Connes. He proposed that the coordinates of spacetime themselves might not commute. In this vision, the universe isn't made of distinct, pinpointable locations. Instead, space and time at their most fundamental level are fuzzy or blurred. This isn't a blurriness due to our poor instruments. It is an intrinsic, fundamental property of reality, a direct consequence of a quantum uncertainty principle for spacetime itself, much like the Heisenberg uncertainty principle that says you cannot know both a particle's position and its momentum with perfect accuracy. To grasp this, don't think of points on a grid. Think instead of a pianist playing a chord. The chord is a single, rich sound, but it is composed of multiple individual notes played together. You cannot separate the chord into its constituent notes without changing the sound itself. In non-commutative geometry, a point in this fuzzy spacetime is like that chord. It's not a location, it's a spectrum of possibilities, and the order in which you try to measure its properties fundamentally changes what you observe. This has a staggering implication. The continuous, smooth spacetime of Einstein's relativity emerges only as a large-scale approximation, much like the smooth surface of a pond emerges from the chaotic motion of countless water molecules. The true, fundamental nature of reality is a seething, non-commutative quantum geometry. The breathtaking power of this framework is how it naturally and elegantly incorporates the existence of extra dimensions, not as curled-up little circles, but as intrinsic properties of this fuzzy geometric algebra. In Kahn's work, the additional dimensions needed to describe the forces and particles of the standard model aren't spatial in the way we normally think. They are internal dimensions encoded directly into the non-commutative properties of the coordinates themselves. The mathematical structure that describes this fuzzy spacetime automatically has extra components, and these components correspond perfectly to the properties of the Higgs field, the gauge bosons, and even the different families of fermions that make up our universe. In one of the most stunning achievements in theoretical physics, Kahn and his collaborators used this approach to almost derive the entire standard model of particle physics from pure geometry. The electromagnetic force, the weak force, the strong force, and the Higgs mechanism, all of it emerges naturally from the requirements of a non-commutative, higher dimensional geometry. The particles we see aren't just moving in space, they are vibrational modes of this geometric structure. The forces aren't interactions between particles, they are the curvature of this fuzzy spacetime. It is a vision of breathtaking unity, where the entire zoo of particles and forces is revealed to be nothing more than the harmonic language of a deeper geometric reality. This isn't just adding hidden dimensions to our universe, it is showing that the universe in its entirety is a geometric object in a space where the old rules of measurement no longer apply, revealing a hidden elegance at the heart of all things. Yet if the intricate non-commutative dance of fuzzy coordinates suggests a deeper layer beneath spacetime, the next theory takes this idea to its ultimate conclusion. It proposes that space and time, and the very dimensions that define them, are not fundamental ingredients of the universe at all. They are illusions, a collective mirage that emerges from a vast, invisible network of quantum connections. This is the emergent spacetime paradigm, a view that turns our understanding of reality inside out. For centuries, physics has treated spacetime as the ultimate stage, the fixed and immutable background upon which the drama of particles and forces plays out. Einstein's great insight was that this stage isn't rigid. It can warp and curve, but it still exists as a fundamental entity. The emergent paradigm challenges this at the deepest level. It suggests that the stage itself is built out of something else entirely. Think of temperature. When you feel the warmth of a cup of coffee, you're not sensing a fundamental substance called heat. You're experiencing the collective, average kinetic energy of trillions of jostling water molecules. Temperature is an emergent property. It doesn't exist for a single molecule, only for a vast ensemble of them. Proponents of emergent spacetime argue that our experience of a smooth, continuous, four-dimensional universe is exactly the same kind of phenomenon. It's a convenient, large-scale approximation that arises from the incomprehensibly complex interactions of countless more basic quantum building blocks. So, if spacetime isn't fundamental, what is? The leading candidates are quantum information and entanglement. Imagine the fundamental constituents of reality are not tiny vibrating strings or loops, but simple, abstract quantum bits or qubits. These qubits have no inherent location in space. They simply exist in a vast, abstract network of quantum connections. Now, recall the bizarre phenomenon of quantum entanglement, where two particles become linked so that affecting one instantly affects the other, regardless of distance. The emergent spacetime paradigm proposes that this spooky action at a distance isn't action taking place in space. It is what creates the very notion of space and distance in the first place. The amount of entanglement between different sets of these qubits can literally define their geometric separation. Two highly entangled qubits are interpreted as being very close together in the emergent spatial geometry. Two qubits with very little entanglement between them are interpreted as being very far apart. In this breathtaking vision, space isn't a container, it is a web of relationships. The three-dimensional world we move through is a kind of holographic projection, a simplified map we create to make sense of an underlying, incomprehensibly complex network of quantum information. This perspective finds powerful support in the AD/CFT correspondence we discussed earlier, which shows a perfect duality between a theory of gravity in a volume of space and a quantum field theory without gravity living on its lower dimensional boundary. The gravity and the geometry in the volume are entirely encoded in and emerge from the entangled quantum information on the boundary. This has a profound implication for the nature of dimensionality itself. The fact that we perceive exactly three spatial dimensions and one time dimension is not a law written into the foundation of the cosmos. It is a consequence of the specific way the entanglement is organized within the fundamental quantum network. Different patterns of entanglement could give rise to universes with different numbers of large, emergent dimensions. Our cosmic configuration just happens to be the one that results in a stable, classical world where galaxies, planets, and life can form. At the very smallest scales, near the Planck length, this smooth geometric picture is expected to break down. The concept of a continuous dimension would dissolve, replaced by a chaotic, fluctuating froth where notions of here and there become meaningless. In this fundamental realm, there is no space and no time as we know them, only a dynamic, ever-changing web of quantum information from which our familiar reality periodically crystallizes. This paradigm doesn't just add hidden dimensions, it suggests that dimensionality itself is a derivative concept, a useful tool for navigating a world that is, at its heart, something far more strange and interconnected. But if the idea of a universe emerging from a quantum network of information seems to redefine the very essence of reality, our next theory takes us back to one of the most elegant and powerful principles in all of physics: symmetry. We've long known that the fundamental forces we observe today were once unified in the searing heat of the Big Bang, and that they differentiated as the universe cooled through a process of symmetry breaking. The symmetry theory of dimensions proposes a breathtaking extension of this idea, suggesting that the very dimensionality of our universe, the fact that we have exactly three large spatial dimensions, is itself the frozen result of a cosmic symmetry breaking event. Imagine the earliest moments of the cosmos, a state of unimaginable energy and perfect symmetry. In this primordial fireball, all forces were one, all particles were massless, and the very concept of distinct dimensions may not have existed. The universe could have begun in a state of perfect, higher dimensional symmetry, perhaps with 10 or 11 dimensions all existing on an equal footing, all expansive and uncurled. This configuration would have possessed a beautiful mathematical perfection, but like a pencil balanced perfectly on its tip, it was inherently unstable. As the universe expanded and cooled, it had to choose a stable, lower energy state. It underwent a phase transition, a cosmic freezing that locked the exuberant energy of creation into a more stable, but less symmetric form. This is analogous to what happens when water freezes into ice. Liquid water is highly symmetric. It looks the same in every direction, but when it freezes, it crystallizes into a specific, rigid lattice structure. This ice crystal has a different, lower kind of symmetry than the water it came from. The symmetry theory of dimensions posits that our observable universe is the cosmic equivalent of that ice crystal. The hot, symmetric, higher dimensional state froze, and in doing so, it had to choose which dimensions would become our large, familiar space, and which would be relegated to a tiny, compactified existence. The specific outcome, three large spatial dimensions and 6 small ones, wasn't a random draw. It was likely the result of dynamical stability. Physicists can model this process using the mathematics of quantum field theory applied to the fields that describe the geometry of spacetime itself. They find that certain configurations are dynamically preferred, meaning they represent the lowest energy states, the valleys in the landscape of cosmic possibility. A universe with fewer than 3 large dimensions might be too simple to support the complex structures needed for stability, like the intricate orbital mechanics that allow for solar systems. A universe with more than 3 large dimensions might be inherently unstable at the quantum level, causing forces like electromagnetism to weaken so drastically that atoms and molecules could never form. The number 3 appears to be a Goldilocks dimension, not too few, not too many, but just right for a rich, complex, and long-lived universe to emerge from the chaos. This perspective offers a profound answer to the question of why we perceive the dimensions we do. It's not that other dimensionalities are impossible. It's that a universe with 3 large spatial dimensions represents a deep and stable valley in the thermodynamic history of the cosmos. It was the most likely outcome, the path of least resistance for a cooling, expanding universe seeking a stable equilibrium. The symmetry was broken, the dice were cast, and the result was a cosmos with a specific architectural blueprint, one that, purely by the laws of physics and probability, was predisposed to eventually give rise to beings who could look back and wonder at the elegant, broken symmetry that made their existence possible. But if the very laws of physics and the stability of dimensions can be explained by cosmic phase transitions, we are still left with one of the most unsettling and profound puzzles in all of cosmology. Why does any of this orderly complexity exist at all? This brings us to a thought experiment so bizarre it threatens to undermine our entire conception of reality, forcing us to confront the ultimate implications of a universe governed by probability and eternity. This is the Boltzmann-Brane paradox, and its resolution may be intimately tied to the specific dimensional architecture we call home. The paradox is named for Ludwig Boltzmann, the 19th-century physicist who helped pioneer statistical mechanics. He proposed that the overwhelming order we see in our universe, from the structured spiral of a galaxy to the intricate machinery of a living cell, might not be the default state. In an eternally existing universe, or even in a vast multiverse, the most common state by far is one of maximum disorder, a featureless sea of particles in thermal equilibrium known as heat death. But Boltzmann realized that even in this ultimate state of chaos, random quantum fluctuations could, by sheer unimaginable luck, cause particles to momentarily arrange themselves into any configuration, no matter how complex. Given enough time, literally anything that is not strictly forbidden by physics will eventually happen through a random fluctuation. A fully formed starship could pop into existence. An entire planet with a complete history could blink into being. Or, and this is the crux of the paradox, a single, self-aware brain could fluctuate into existence, complete with all the memories and sensory impressions of a coherent life, believing itself to be a person living in an ordered world, when in reality it is just a momentary, solitary accident in an endless, mindless void. The terrifying implication is that statistically, over an infinite timeline, the number of these random Boltzmann brains should utterly swamp the number of ordinary, evolved observers like us who arose from a sustained, ordered cosmic history. It is infinitely more likely for a single brain to fluctuate into existence than for an entire 13.8 billion-year-old universe with billions of galaxies to evolve naturally. So why do we observe the latter? Why does it seem we are part of a long, coherent, lawful history, and not just a fleeting flicker of consciousness in the dark? This is the Boltzmann-Brane paradox, and it suggests that our most basic confidence in an objective reality is fundamentally flawed. This is where the landscape of string theory and the nature of our universe's dimensions offer a potential escape route. The vacuum of our universe is not a passive emptiness. It is a specific, structured state defined by the particular way its 6 hidden dimensions are curled into a Calabi-Yau shape. This vacuum has a very specific, incredibly low energy value. This is not an accident, it is a key piece of the puzzle. A universe with a positive cosmological constant like ours is inherently metastable. It is not in a true, eternal equilibrium. Eventually, through quantum tunneling, it could decay into a lower energy, more stable vacuum state. This process has a finite, calculable timescale. Now compare that to the timescale required for a Boltzmann brane to randomly fluctuate into existence. The probability is so vanishingly small that the average time you'd have to wait for one is exponentially longer than the expected lifetime of our current vacuum state. Our universe, with its specific dimensional arrangement and cosmological constant, is fundamentally unstable on a long enough timeline. It will likely decay into a different state long before the conditions ever become statistically ripe for the spontaneous generation of Boltzmann branes within it. In other words, the clock is ticking on our cosmic environment, and it will run out long before such absurdly improbable fluctuations can become likely. We don't see Boltzmann branes because our universe isn't old enough or stable enough to produce them in any significant number. This suggests a profound connection between dimensionality and observable reality. The specific way our extra dimensions are compactified doesn't just determine the masses of particles and the strength of forces, it also sets the decay rate of our vacuum. A universe that allows for the long-term, stable existence of complex structures like galaxies and planets must, by its very construction, be one that is inherently unstable on a cosmological timescale, thereby suppressing the probability of these paradoxical fluctuations. The dimensional arrangement that makes our lives possible also protects us from the existential nightmare of being mere momentary illusions. We are not Boltzmann branes because we live in a universe whose physical parameters, forged in the geometry of hidden dimensions, create a Goldilocks zone not just for life, but for coherent, sustained reality itself. Our existence is evidence of a cosmos built not for eternity, but for a meaningful, if temporary, story. For decades, these theories of hidden dimensions have lived primarily in the realm of mathematics and imagination. But what if we could actually test them? What if we could devise experiments to reach beyond our three-dimensional prison and feel the edges of these unseen realms? This is not science fiction. It is the cutting edge of modern physics, where theorists and experimentalists are collaborating on a breathtaking hunt for the first tangible evidence that our universe is so much more than it appears. The most powerful tool in this search is without a doubt the Large Hadron Collider, the LHC. By smashing protons together at velocities approaching the speed of light, this colossal machine recreates for a fleeting instant the unimaginable energies of the early universe. In these violent collisions, the LHC isn't just looking for new particles, it's probing the very structure of spacetime. One of the most dramatic signatures it hunts for is the creation of microscopic black holes. In our standard four-dimensional universe, making a black hole requires compressing a huge amount of mass into a tiny volume. But if the large extra dimensions model is correct, and the true scale of quantum gravity is much lower, then the LHC could have enough energy to create them. These wouldn't be the cosmic monsters that devour stars. They would be tiny, quantum-sized black holes that would evaporate instantly in a spectacular, predictable shower of particles. A clear and unmistakable signal that we've tapped into the physics of higher dimensions. Alongside this, physicists are meticulously searching for events with missing energy. This occurs when the energy and momentum of the particles going into a collision don't perfectly match the energy and momentum of the particles coming out. In our world, this is impossible. Energy must be conserved. But if a graviton or another particle produced in the smash were to carry that energy away into a hidden dimension, it would appear to us as if a portion of the collision's energy simply vanished into thin air. It would be the ultimate cosmic magic trick, and finding its source would revolutionize our understanding of reality. While the LHC probes the high-energy frontier, another equally fascinating search is happening on an incredibly small scale, using exquisitely precise tabletop experiments. These aren't massive, miles-long tunnels. They are devices small enough to fit on a lab bench, designed to test the law of gravity itself at distances smaller than a human hair. The reasoning is simple. If there are large extra dimensions, gravity should stop following Isaac Newton's famous inverse square law at these tiny scales. Imagine gravity's force spreading out like the light from a bulb. In 3 dimensions, the light spreads over the surface of an ever-growing sphere, and its intensity diminishes with the square of the distance. But if there's a 4th spatial dimension, the light would spread out into an even larger 4-dimensional volume, diminishing much faster. These experiments use incredibly sensitive pendulums or torsion balances to measure the gravitational attraction between 2 objects as they are brought closer and closer together. They are literally trying to feel the moment when gravity's strength changes, the moment it begins to leak into a hidden dimension. It is a painstaking, delicate search for a deviation so small it would be easy to miss, yet its discovery would be one of the most profound in the history of science. The cosmos itself provides its own natural laboratory through the cataclysmic collisions of black holes and neutron stars, events so powerful they send ripples through the fabric of spacetime itself, gravitational waves. Observatories like LIGO and Virgo have opened an entirely new window on the universe by detecting these waves. Now, scientists are using them to search for hidden dimensions in a new way. The idea is that if extra dimensions exist, gravitational waves might leak into them as they travel across the universe. This leakage would subtly alter the waves, changing how they attenuate over distance in a specific way that wouldn't happen if gravity were confined to our 3-dimensional brain. By carefully analyzing the signals from these distant mergers, astronomers can look for these telltale modifications, using the universe's most violent events to probe its most secret geometry. The future of this search is even more exciting. The upcoming Laser Interferometer Space Antenna, or LISA, will be a space-based gravitational wave observatory sensitive to a much lower frequency range. This will allow it to detect the mergers of supermassive black holes, events that generate waves which travel for millions of years before reaching us. This incredibly long journey gives any potential leakage into extra dimensions more time to leave its imprint, making the signal much clearer. Furthermore, next-generation particle colliders, envisioned to be several times more powerful than the LHC, would push the energy frontier even further, dramatically increasing the chances of creating those microscopic black holes or detecting the heavy Kaluza-Klein partners predicted by universal extra dimensions. We are living in a golden age of exploration, not of new continents but of new dimensions. Every time the LHC smashes protons, every time a torsion balance measures a force at a microscopic distance, and every time we observe the ripple from a black hole collision, we are conducting an experiment on the fundamental architecture of reality. We may be on the verge of a discovery that would dwarf all others, a revelation that the world we see is merely the surface of an infinitely richer, deeper, and more magnificent cosmos. The hidden dimensions may be just out of reach, but for the first time in human history, we are building the tools that might finally allow us to touch them. From the elegant, curled-up dimensions of Kaluza and Klein to the vast, warped geometry of the Randall-Sundrum model, from the vibrating strings that demand 10 dimensions to the quantum loops that weave the fabric of spacetime itself, our journey through these 30 theories reveals an incredible tapestry of human imagination and intellect. We've ventured into a landscape where our entire universe might be a holographic projection, a membrane floating in a higher dimensional bulk, or even a single possibility in an infinite mathematical multiverse. We've seen how the search for hidden dimensions is inextricably linked to our greatest mysteries, from the baffling weakness of gravity to the invisible presence of dark matter. What's truly breathtaking is that this isn't a single, unified quest. It is a glorious, sprawling ecosystem of ideas, a testament to the fact that when faced with the unknown, the human mind doesn't just find one path forward, it finds dozens. The mathematician finds beauty in the equations of non-commutative geometry. The physicist finds promise in the predictive power of supersymmetry. The cosmologist finds clues in the faint afterglow of the Big Bang. Each approach is a different language attempting to describe the same profound truth. That reality is far grander and more mysterious than our everyday experience suggests. Yet, for all their brilliance, these ideas remain in the realm of theory. We have not yet seen a graviton, detected a Kaluza-Klein particle, or measured gravity deviating from its familiar law at microscopic scales. But that is the very heart of science, the courageous act of building castles in the air, and then painstakingly trying to put foundations under them. These theories are not mere speculation, they are a necessary and vital part of the scientific process. They are the maps we draw of uncharted territory, guided by the few clues we have, hoping they will lead us to the shore of a new world. And for the first time in human history, we are building the ships that can take us there. The Large Hadron Collider, with its cathedral-like detectors, is not just a machine of discovery but a vessel for dimensional exploration. The exquisitely sensitive tabletop experiments measuring the force of gravity at the width of a human hair are our most delicate probes into the fabric of space. The gravitational wave observatories listening to the echoes of black hole collisions are, in effect, listening for the subtle acoustics of the cosmos's hidden architecture. The journey is far from over. In fact, it has just begun. The greatest discovery may not be a single eureka, a moment, but a gradual dawning, a collective realization that the clues were there all along, waiting for us to become clever enough to understand them. So stay curious. The next headline you read about a strange signal at a particle collider, or a new measurement of gravitational waves, or an unexpected result in a quantum lab, might not just be news about a new particle. It might be the first tremors of a dimensional revolution, the first glimpse into the deeper, richer, and more magnificent cosmos that has been hiding in plain sight all this time. The greatest story ever told is the story of the universe itself, and we are only just starting to read past the introduction.